Salam alaikum again.
عليكم السلام ورحمة الله.
Salam alaikum. Okay,
وعليكم السلام ورحمة الله وبركاته.
thank you. All right. Uh, in other models, I told you Erring model. The Erring model is also an advanced acceleration model used for when we have multiple stress factors influence the reliability of the systems. Um, uh, in contrast of simpler models that consider only one stress variable, the Airing model can incorporate several factors such as temperature, voltage, and humidity at the same time. It will consider a semi-empirical model because it combines theoretical principles from physics with experimental observations to describe failure behavior more accurately. This makes it essentially useful in complex systems where failures are caused by the interaction of multiple environmental stress. By accounting for these combined effects, the Airing model provides a more realistic and precise prediction of product lifetime under normal operating conditions. So it will be um, consider all of those factors, at the same time. So it is widely used in reliability analysis for electronic components and material exposed to diverse environmental conditions. So, um, inshallah, next week I will show you in some example these models and how it works. We have another model, the inverse power law model is commonly used in reliability engineering to describe how a product's lifetime changes in response to applied mechanical or electrical stress. The fundamental concept of this model is that as the stress level increase, the lifetime of the product will decrease in a predictable way, following an inverse power relationship. This makes it particularly useful for analyzing failure caused by fatigue or electrical stress or mechanical loading and so on. And you often use this model in applications such as insulation breakdown and mechanical fatigue testing and so on. One of the main advantages of the inverse power law model is its simplicity, which makes it easy to apply while still providing reliable insights into how stress impacts product durability and lifespan. All right. Step stress testing. This is a type of accelerated life testing where the stress applied to a product will be increase gradually in steps over time. So the test typically begins at a lower stress level, allowing the product to operate under relatively mild conditions, and then the stress is increased at predefined intervals until failures occurs. This method helps you observe how a product behaves under varying stress levels and identify critical thresholds where failures begin to occur. And step stress testing is efficient because it makes better use of limited samples and provides detailed information about failure mechanisms across different stress conditions. It is especially useful when you want to understand how incremental increases in stress impact reliability. Okay. We have a constant stress testing, which is a method in in a product is subject to a fixed level of stress for the entire duration of the test. Unlike step stress testing, where stress levels change over time, this approach maintains consistent conditions such as temperature, voltage, or mechanical load through the experiment. The main goal is to observe how long the product lasts under that specific stress level and to measure the time to failure. This method is particularly useful for obtaining clean and consistent data, which simplifies the analysis and modeling process. And because the stress remains constant, it is easier to compare results across different samples and apply statistical methods to estimate reliability with greater confidence. Accelerated live testing offers several important advantages that make it a valuable tool in reliability engineering. One of the primary benefits is the significant reduction in testing time, as applying higher stress levels allows failures to occur much faster than under normal conditions. This, uh, uh, one second, yeah. This also leads to lower overall testing costs since long-term testing can be expensive and resource intensive. ILT enables you to detect potential failures early in the development process, allowing them to improve product design before mass production. As a result, it enhances overall product reliability and supports faster development cycles, helping companies bring high quality products to market more efficiently. Although accelerated live testing is a powerful method, it has several important limitations that must be considered. One major challenge is that ILT relies heavily on the accuracy of acceleration models, and incorrect assumptions can lead to misleading results. Additionally, applying very high stress levels may introduce failure mechanisms that do not occur under normal operating conditions, which can reduce the validity of the results. There is also a risk of errors when extrapolating data from accelerated conditions back to normal usage. Furthermore, ILT often requires specialized equipment and technical expertise, which can increase setup cost. Finally, this method is not suitable for all types of products or failure mechanisms, so it must be applied carefully and appropriately regarding the input data and all of the system conditions. All right. To better understand accelerated live testing, consider a case study involving an electronic component such as a capacitor. In this example, the component is subjected to evaluated stress conditions, including higher temperature and increased voltage to accelerate the aging process and induce failures more quickly. A constant stress IRT method is used where the stress levels remain fixed throughout the test, and the primary goal is to estimate the component's lifetime under normal operating conditions by analyzing failure data collected during the test. Once the failure times are recorded, a reliability model such as the variable distribution can be fitted to the data. Finally, using an appropriate acceleration model, the results are extrapolated to predict the expected lifetime under standard conditions and providing valuable insights into product reliability. Uh, in the section 4 is related to test planning and sampling importance of test planning. Uh, uh, I want to say that test planning also is a crucial steps in reliability testing because it ensures that the entire testing process is structured, efficient, and goal-oriented. A well-designed test plan clearly defines the objectives of the study, helping you focus on the most important reliability aspects. Let me add a new student. And so uh, also it can ensures efficient use of resources, including time, equipment, and samples, which is especially important when testing can be costly or time consuming. And proper planning improves the accuracy and reliability of the result by minimizing errors and uncertainties during the testing. Additionally, it helps in selecting appropriate testing methods and sampling strategies, ensuring that the collected data will be meaningful and suitable for our analysis. In overall, I want to say that effective testing planning is very essential for obtaining valid and actionable reliability insights. Okay. Defining the clear and precise objective is one of the most important steps in reliability test planning. The objectives determine the overall directions of the test and ensure that all activities are aligned with the intended goals. This includes specifying the purpose of the test, such as evaluating product lifetime or identifying potential failure models, and you must also define the performance criteria and reliability targets such as minimum acceptable mean time between failure or expected lifespan. In addition, it is important to establish the test conditions, including stress level, environmental factors, and operational constraints. By clearly defining these objectives at the beginning, the testing process becomes more focused and efficient and capable of producing meaningful and actionable results. Uh, Another topic is sample size determination. Determining the appropriate sample size is also a crucial aspects of test planning in reliability engineering. The sample size refers to the number of units that will be tested to obtain statistically meaningful results. You can consider a very big sample size or very small sample size. You can increase your accuracy, but the problem is that you will face a lot of problems such as memory and big data will take over a lot of times and uh, reduce the accuracy of the decision making and so many things. So you have to find a trade-off between the um, how many how much what is the sample size is suitable for your case study, and it depends on the several factors, including the desire, um, confidence level, and level of precision required, and the expected failure rate of the product. A larger sample size generally leads to more accurate and reliable results, as it reduces uncertainty and variability in the data. However, increasing the sample size also increases the cost and resources required for testing. Therefore, you must carefully balance cost and accuracy when deciding on the sample size, ensuring that the test results are both statistically valid and practically feasible. All right. Statistical confidence is an important concept in reliability testing that reflects how certain we are about the result obtained from a test. It is typically expressed as a percentage such as 90% or 95% and indicates the probability that the true value of a parameter lies within a specified range. Higher confidence levels provide greater assurance in the results, but they also require larger sample sizes and more data. This introduces a trade-off between confidence and testing cost, and statistical confidence is closely related to confidence intervals, which define the range within which the true parameter is expected to lie. And understanding statistical confidence helps you quantify uncertainty and make more informed decision based on test results. And so sampling methods are, um, as I told you, essential in reliability testing because they determine how representative the test data will be. In random sampling, every unit in the population has an equal chance of being selected, which helps reduce bias and provides a fair representation of the overall system. This method is simple to implement and is commonly used in many applications. On the other hand, um, uh, stratified sampling involves diving the population into distinct subgroups or based on specified characteristics such as manufacturing batch or operating conditions. And samples are then selected from each subgroup to ensure that all categories are adequately represented. This approach is especially useful when the population is not homogeneous and helps improve the accuracy and reliability of the test results. Okay, sequential testing. In sequential testing also is a flexible and efficient testing approach where decisions are made progressively as data is collected. And instead of fixing a large sample size in advance, tests are conducted one sample at a time or in small groups, and the results are analyzed continuously. Based on the observed outcomes, a decision is made to either accept and the product, reject it, or continue testing. This method can significantly reduce both the number of samples required and overall testing time, making it more cost effective compared to traditional fixed sample testings. Sequential testing is particularly useful when early results clearly indicate whether a product meets reliability requirements, allowing you to make faster and more efficient decisions. So another concept is reliability demonstration testing, or RDT, is used to verify whether a product meets predefined reliability requirements with a specified level of confidence or not. In this type of testing, a set of number of units can be tested under defined conditions, and the number of failures also can be carefully observed. And the results are then compared against a target reliability level to determine whether the product satisfies the required performance criteria or not. If the product meets the target with sufficient statistical confidence, it is accepted. Otherwise, it may be rejected or require further improvement. RDT is commonly used in industries where reliability is critical, such as aerospace, defense, and electronics, as it provides a structure and quantitative way to validate product reliability claims. Test duration planning also is an important part of designing a reliability test, and as it determines how long the testing process will continue, and the duration depends on several factors, including the reliability objectives, the level of stress applied during testing, and expected time to failure of the product. In general, the longer test duration provide more accurate and reliable data because it allow more time for failures to occur and be analyzed. However, longer tests also require more resources and increase overall cost. On the other hand, shorter tests can reduce time and expense, but may result in less data and lower confidence in the results. Therefore, you must carefully balance accuracy, time, and cost when planning the test duration to ensure meaningful and efficient testing outcomes. Okay, resource allocation is a critical part of the testing planning, as it ensures that all necessary resources are used efficiently throughout the reliability testing process. This includes human resources such as skilled engineer and technician who design and conduct the test, as well as equipment like testing machines and measurement tools required for data collections. Budget is another important factor, as reliability testing can be costly depending on the complexity and duration of the test, and time management is also essential to ensure that testing is completed within the required schedule, and proper resource allocations helps optimize performance, reduce waste, and ensure that the testing process is both effective and cost efficient while still achieving the desired reliability objectives. All right. Risk and considerations also are in an essential part of reliability test planning, as they help identify and manage potential issues that could affect the source of the testing process. Uh, this risk can be technical, such as equipment malfunction or incorrect modeling assumptions, operational such as human error or process inefficiencies, or financial such as exceeding the allocated budget. It is important to assess both the likelihood and the potential impact of each risk to understand its significance. Once identified, appropriate mitigation strategies can be implemented, including backup plans, safety measures, and continuous monitoring. By proactively managing risk, you can ensure a smoother testing process and improve the overall reliability and validity of the results. Another in the section 5, I want to explain about data collection and data quality. Let me add. All right. Data quality is a critical factor in reliability analysis because the accuracy of any conclusions depends on directly on the quality of the data collected, and high quality data ensures that the analysis reflects the true behavior of the system and reduces errors in modeling and prediction. If the data is inaccurate, incomplete, or inconsistent, the resulting reliability estimates may be misleading and lead to poor engineering decisions. And good data quality include attributes such as accuracy, completeness, consistency, and validity. By maintaining high standards in data collections and management, you can ensure that your reliability analysis is trustworthy, and that the conclusions drawn from it can be meaningful and also actionable. You can rely on these results. In reliability analysis, data can be categorized into uh, different types depending on how it is collected and what information it contains. Failure time data represent the exact time at which a system or component fails, and is the most straightforward type of the data. However, in many real-world situations, not all units fail during the test period, leading to sensor data where only partial information is available. So we have some limitation here. Suspension data refers to units that are removed from the test before failure occurs, often due to time or resource constraints. Additionally, data can sometimes be grouped into intervals rather than recorded as exact values, which is known as group data. Each of these data types requires different analytical approaches, and selecting the correct method is very essential for accurate reliability estimations. Complete data refer to a situation in reliability testing where all tested units have failed, and the exact failure time for each unit also is non-variable. This type of data provides full and precise information, making it highly valuable for statistical analysis. Since there are no missing or sensor observations, complete data allows for straightforward application of reliability models and often results in higher accuracy when estimating parameters such as failure rate and lifetime distributions can be taken into account. However, in practice, obtaining complete data can be challenging, as it may require long testing periods to ensure that all units fails. As a result, complete data is less common in real-world applications, but when available, it significantly simplifies the analysis process and improves the reliability of the results. Sensor data is a very common occurrence in reliability testing and refers to situations where the exact failures times of unit is not fully observed. This often happens when a test is stopped before all units have failed, or when some units are removed from the test for various reasons, such as time constraints or resource limitations. And instead of exact failure times, only partial information is available, such as knowing that a unit has survived up to a certain point, and a proper handling of sensor data is essential, because ignoring it can be lead to bias or inaccurate reliability estimates. There are different types of sensor data, including right sensor, left sensor, and interval sensor data, each requiring a specific analytical approaches to ensure accurate reliability analysis. All right, right sensor data occurs when a test ends before a unit experience failure, meaning that the exact failure time is unknown, but is known to be behind a certain point. For example, if a component is still functioning at the end of the testing period, we only know that its lifetime exceeds the duration of the test. This type of censoring is very common in reliability testing, because it is often impractical to wait for all units to fail. Right sensor data provides valuable partial information and should always be included in the analysis to avoid biased results. Proper statistical methods are required to incorporate this type of data, ensuring that reliability estimates remain accurate and representative of the system's true performance. Left sensor data occurs when a failure has already happened before the observation or testing begins, and meaning that the exact time of the failure is unknown, but is known to be earlier than a certain point. So, for example, if a component is found to be defective at the start of the testing without knowing when it actually failed, it is considered left sensors. And this type of data can arise when there is limited information about the period usage or history of a component, or when failures are detected late. Although it is less common than right sensor data, it is still plays an important role in reliability analysis, and proper statistical techniques are required to handle left sensor data to ensure that reliability estimates remain accurate and unbiased. We have interval sensor data occurs when the exact time of failures is unknown, but it is known to have occurred within a specific time interval. This situation often arises when systems are inspected at regular intervals rather than continuously. For example, if a component is checked at the beginning and end of the time period and is found to have failed during that interval, the exact failure time is not known, only that it occurred between the two observations. This type of data is common in real-world reliability testings, where continuous monitoring is not feasible, and however it provides only partial information. Interval sensor data is still valuable and must be properly incorporated into reliability analysis using appropriate statistical methods to ensure accurate results. So another thing is that the data recording methods. Data recording methods also play a critical role in ensuring that reliability data is captured accurately and efficiently. Traditional manual recording involves a human entry of data into logs or spreadsheets, which can be simple but is more prone to human error. In contrast, automated recording uses sensors and data acquisition systems to collect data continuously and with higher precision, reducing the likelihood of mistakes. Modern systems often store data in digital data sets, allowing for centralized management, easy access, and efficient analysis. Regardless of the method used, it is essential that the data is recorded with high levels of accuracy, consistency, and where possible in real time to ensure that the reliability analysis is based on trustworthy information. In reliability testing, several common data issues can affect the quality and accuracy of the analysis. Missing data occurs when some observations are not recorded, which can lead to incomplete insights if not handled properly. Inaccurate data may result from measurement errors or incorrect recording, leading to misleading conclusions. Inconsistent data arises when information is recorded in different formats or contains conflicting values, making analysis more difficult. And um, this is can be which are extreme or use unusual values can uh, distort the statistical results if not properly identified and treated. Additionally, data bias can occur when the sample is not representative of the overall population, leading to skewed results. And addressing these issues is very essential to ensure reliable and valid analysis outcomes. So we have a data pre-processing. Also, this is a very critical steps in reliability analysis that involves preparing raw data for accurate and effective evaluation. And this process include several important steps, starting with data cleaning, where errors, missing values, and inconsistencies are identified and corrected or removed. And data transformation may also be applied to standardize or normalize values, making them suitable for analysis. Additionally, outliers and noise must be handled carefully to avoid distorting the result. And in some cases, data from different sources is integrated and properly formatted to ensure consistency. By performing through data processing, you can significantly improve the quality of the data set and leading to more reliable models and more accurate conclusions in reliability analysis. So I want to close the session here, and next week we will keep continue from slide uh, 54. All right. Do you have any question or
Thank you, Doctor.
thank you so
Thanks.
much. Actually, I want to say another things. Next Monday, I cannot be, I cannot deliver my lecture. So I will ask in the in the blackboard if you are okay to just postpone my lecture to Tuesday if everybody are okay, or Wednesday at the same time, you know. So I will send a message, and this lecture will be online because I know very difficult um, to satisfy everybody to be in the class, in if when you are changing the time.
Okay, sounds good.
Yes. I will send a message and I will
Okay, that's
ask.
fine, no problem.
Okay,
Dr.
okay.
Salam alaikum.
Salam
Thank you so
alaikum.
much for your presentation. Thank you so much for opening this discussion with us.
Thank you.
This is Fahd Al Qahtani. I just want you to be, to consider that during this, unstable situation that we have,
Yes. Yes.
geopolitical situations that we have been through,
Yes.
it's difficult for us to have, physical, let's say, physical classes.
Yeah, no problem.
And
As I
yeah,
mentioned, next Monday, I will I wanna postpone next Monday lecture to Tuesday, and I will ask everybody if you are available at the same time at 4:30 online. Because
yes,
it seems that everybody are available online. I can have. However, for me, I would like to see physically everybody in the class. So, and because I'm enjoying in discussion with students, but it seems that more students are will be online. Even in online sessions, six students are not available. So I don't know where are there. Because